Hi everyone, and welcome to this short video about advanced integration. In this video, we will talk about cases where normal integration, as you learned it, does not work. Therefore, we will introduce two special types of integrating, namely integration by parts and integration by substitution. We will closely take a look at them and discuss one example for each in detail together. Finally, there are also some exercises awaiting you at the end of this video with which you can train and test your knowledge. So let's start with the content. You previously learned how to calculate integrals. The usual way is that you search for the antiderivative of a function and then calculate with it. But now imagine the following cases where you want to integrate the function x times e to the power of x, or the function x times the square root of x plus 1 to the power of 3. Usually, we would try to find the antiderivative now, but this seems to be a problem here. Here we cannot simply apply our previously learned rules for finding the antiderivatives. Therefore, we need another solution. Luckily, there are two tricks that we can use here, which are both really cool. One of them is called integration by parts, and the other one is called integration by substitution. But how do they work, and in which cases should we use which one of them? Let's start with integration by parts. Integration by parts is a really nice method when we want to integrate a product of functions. This means that the function that we are integrating can be divided into two functions that are multiplied. Integration by parts is defined as follows. The integral from a to b of the derivative of f of x times g of x dx is equal to, in squared brackets, f of x times g of x with the limits b and a, minus the integral from a to b of f of x times the derivative of g of x dx. Looks complicated at first, but actually you should be familiar with all the subparts. You know what a function is, what a derivative is, you know the notion of integrals, as well as the notion in the squared brackets. Nevertheless, let's take this apart and understand what we really have to do here. We will walk through integration by parts step by step. The formula you just saw is written above in the red box. The left side is always where we start off when we get a task with an integral. So we have an integral of the product of two functions. In the first step, we need to choose which one of them is f prime of x and which one is g of x. This is the base for the further calculation. In the next step, we need to calculate f of x and g prime of x, as we will need them on the right side of our equation. So for f prime of x, we will need to find the antiderivative, while for g of x, we need to find the derivative. After we have done that, we can simply plug in all of that into the formula. The last step is then to calculate until you will reach your final result. This is then done like in basic integration, like using the normal integration rules. Let's go through an example together and discuss every step in detail. Our example is the integral from 0 to 2 of x times e to the power of x dx. We cannot simply find the antiderivative of it with our usual rules, but luckily we can apply integration by parts here, because we have a product of two functions. One of them is x, and the other one is e to the power of x. In the first step, we need to choose which one of them is f prime x and which one is g of x. The question is, how do we do that? If you look at the formula for integration by parts again, which is written in the red box, you can see that in the second part, the light blue one, we have an integral again. This means we will also need to calculate an antiderivative for that integral later on, meaning that we will need to find an antiderivative of f of x times g prime of x. We really don't want to come into problems again with finding this antiderivative, and therefore we want this term to be as easy as possible, so that we just can use the usual rules for finding the antiderivative and don't need to recursively use integration by parts over and over again. The solution is therefore that we test for both functions in our task, so for x and for e to the power of x, what happens if we choose them as g of x. The one that has the easier derivative will then be chosen, because this means that the light blue integral will be easier to calculate. Let's do this for our example. In our example, we could either use x as g of x, which would have the derivative 1. The other option would be using e to the power of x as g of x, but this would have the derivative e to the power of x, which is a lot more complicated. Therefore, we choose x to be our g of x, and consequently e to the power of x will be our f prime of x. We are set and ready for the next step. Next up, in step 2, we need to calculate f of x and g prime of x. This means the following in our example. From f prime of x, which we chose to be e to the power of x, we need to find f of x, which is its antiderivative. Luckily, we know how to do this. The antiderivative of e to the power of x is also e to the power of x. From g of x, we need to calculate g prime of x, which we basically already did. It will yield 1. Now we are already done with all the pre-calculations and can use all of this inside our formula. So let us continue with step 3. In step 3, we want to plug in the terms we calculated in step 1 and 2 into the formula of integration by parts. The color coding should make it a bit clearer here, where you have to plug in which term. All we need is f prime of x, g of x, f of x, and g prime of x, which we just calculated. Now putting them into the formula, we will end up with this. The integral from 0 to 2 of x times e to the power of x dx equals, in squared brackets, e to the power of x for f of x and x for g of x, with the limits 2 and 0, minus the integral from 0 to 2 of e to the power of x for f of x times 1 for g prime of x dx. And now we are almost there. All we have to do now is calculating until we reach the final result. If you don't feel comfortable with this yet, you might want to have a look at the video about basic integration again. But let's start for now. The fourth and last step, as just said, is calculating until we reach the final result. The equation in the middle is the one from the last slide, so it is the formula of integration by parts, just with the terms of our example plugged in already. For the blue part here, we plug in 2 for x and subtract it from it the same, but with 0 plugged in for x. It will yield 2 times e to the power of 2 in total for the blue part. For the pink part, we will perform normal integration. This means we first need to look for its antiderivative. The antiderivative of e to the power of x is e to the power of x, so we will use this here. Then we also need to plug in the limit values, so we plug in 2 and subtract the same plugged in with 0. This will yield e to the power of 2 minus 1, in total for the pink part. Together, we then have 2 times e to the power of 2 minus, in brackets, e to the power of 2 minus 1. In total, this is then e to the power of 2 plus 1. Now we are done. We found our result. Let's recap all the steps again now. This is how you would also write it on paper. We started with the task, which was calculating the integral from 0 to 2 of x times e to the power of x dx. Because it is too complicated to directly find an antiderivative, we decided to use partial integration. Therefore, we make a note here stating that we want to solve it via partial integration, and ideally also write down the formula, which is in dark blue here. What we do then is determining f prime of x and g of x and calculating f of x and g prime of x based on that. Then we plug in these values into our formula and calculate using the normal integration rules. And now we are done. Let us summarize a bit. Integration by parts is a very nice method for integrating and a good option when we have a product of two functions for which we cannot find an antiderivative right away. Although integration by parts looks complicated and we have a long formula, it is in fact not too complicated. You just have to determine which function is which, and then all you need to do is plugging in terms. What you should remember here is the formula and the steps. So now that you have learned about one of the methods for solving complex integrals, let us talk about the other one. Integration by substitution is another way of integrating functions. We can use it to integrate chain functions, or in general, when we face very complex terms that we want to get rid of before searching the antiderivative. It is defined by the following equation. The integral from phi from a to phi from b of f of x dx is equal to the integral from a to b of f from phi from u times phi prime of u du. I'll have to admit that this is not the prettiest formula and can look quite confusing. But don't worry, we will go through it together step by step again. The basic idea is that while we are integrating for the variable x on the left side, we have u on the right side. So what we want to do is replacing something that contains an x with u, thus making the integrating easier. But this means we also have to adapt other things in the integral, for example the limits, as well as what is written inside of our integral. But don't worry, we will tackle this together now. On top, you can see the formula for integration by substitution again. There are several steps we have to perform in order to use this formula. I will shortly go through them now, and then we will look at them into more detail one by one, and go through an example together. The first one is the substitution step. In this step, we will choose something that is disturbing us from our integration process and replace it by the variable u. In the second step, we need to solve the substituted term to x, so we need to do some reformulation so that the x is standing alone on one side. We call this result phi of u. In the third step, we will build the derivative of it, so we calculate phi prime of u. Then, in the fourth step, we will calculate the new limits, as you can see in the formula that the limits are not the same on the left and the right side of the equation. In the fifth step, we will calculate f of phi of u, and finally, in the last step, we can integrate the whole thing. This then works as usual, so we can use the rules that we already know. So now let us take a look at an example and go through all the steps together to really understand what we have to do. Let's imagine the following task. Calculating the integral from 0 to 3 of x times the square root of x plus 1 to the power of 3 dx. Usually, we would want to build the antiderivative of this now, but this is not so easy. The square root is really disturbing here, which is why we want to get rid of it. And this is precisely what step 1 is all about. We choose what we want to get rid of and substitute it with the variable u. In our case, we chose the blue part, thus the square root of x plus 1 equals u. Let's move on to step 2 now. In step 2, we want to solve the equation with the u to x. So we want to solve the square root of x plus 1 equals u to x. In our case, we first need to square the terms, leading to x plus 1 equals u squared, and then we bring the 1 to the other side. And now we are done. We ended up with x equals u squared minus 1. We name this phi of u, so phi of u equals u squared minus 1. Let's continue with the third step. In step 3, we want to calculate the derivative of phi of u. This is a one-liner in our case. We had phi of u equals u to the power of 2 minus 1, and thus phi prime of u equals 2u. We can move on to the next step now, and maybe you remember there were 6 steps in total, so we are already halfway through. In step 4, we want to calculate the new limits. In the formula for integration by substitution, you can see that the initial limits can be defined as phi of b and phi of a. But now we want to have the limits b and a, because they will be the new limits and for the calculation of our integral, given in the formula. How do we do this? We previously calculated phi of u. This was done in step 2, and we came up with phi of u equals u squared minus 1. Now we know from the formula that phi of b is the upper limit and the initial integral. In this case of our example exercise, there's a 3 as the upper limit. This means that phi of b equals 3. And for a, we know that phi of a equals 0, because it is the lower limit in the given integral. We can now solve these equations. As we know that phi of u equals u squared minus 1, this means that phi of b equals b squared minus 1, and for a it means that phi of a equals a squared minus 1. So if we know that phi of b equals 3 and that phi of b equals b squared minus 1, then b squared minus 1 is equals 3. All we need to do now is to solve this equation for b. So we bring the 1 to the right side and take the square root. And we will end up with b equals 2. For a, we do the same. So we have a squared minus 1 equals 0, and then bring the 1 to the other side, take the square root, and finally we'll end up with a equals 1. So to sum step 4 up again, we wanted to calculate the new limits. We can do this with the help of the function phi of u that we previously calculated and with the help of the initial limits which were given in the task. All we do here is plugging in the old limits into the phi of u and then solving it to a and b. Now there's only one step left before the final integration part. Now in step 5 we want to calculate f of phi of u, because our formula tells us that we need it on the right side of the equation for integration by substitution, here marked in green. This looks complicated, but we already have all that it needs. We know what the function f is because it is the one that was given in our task. It is the one inside of the integral we are supposed to calculate. So in our case, f of x is therefore x times the square root of x plus 1 to the power of 3. Now what else do we need? Instead of an x, we have in green phi of u. So it is not f of x, but f of phi of u now. This means we need to replace each x by phi of u now. Luckily, we already calculated phi of u before. As a reminder, we came up with u squared minus 1 for phi of u. This means that if we have f of x equals x times the square root of x plus 1 to the power of 3 and replace all x by phi of u now, we need to replace them by u squared minus 1. This will yield u squared minus 1 times the square root of u squared minus 1 plus 1 to the power of 3. The minus 1 and plus 1 cancel out each other. And then the square root and the to the power of 3 also cancel out each other, and we would have u squared minus 1 times u to the power of 3, which gives us the final result of u to the power of 5 minus u to the power of 3 for f of phi of u. Now we have it all together, and finally, after many pre-calculations, we will be able to plug it all into the formula and calculate the result. We made it to the last step. At the top, you can see the formula for integration by substitution again. The color coding should help you to understand where we need to plug in which value or term. So, in the previous steps, we successfully calculated f of phi of u, which was u to the power of 5 minus u to the power of 3, phi prime of u, which was 2 times u, and the limits a and b, which were 1 and 2. Using our formula, we can now simply plug in the terms. This means that the integral from 0 to 3 of x times the square root of x plus 1 to the power of 3 dx is equal to the integral from 1 to 2 of u to the power of 5 minus u to the power of 3 times 2u du. At this point, all we need to do is calculating the integral as usual. Now, after this transformation we made, it should also be easy to find the antiderivative. Let's do this together for our example exercise. So in the first step, we multiply the green and the pink parts together, because this makes things a lot easier. Then we will have the integral from 1 to 2 of 2u to the power of 6 minus 2u to the power of 4 du. Now we can apply the normal rules to find an antiderivative of this. The result will be 2u to the power of 7 divided by 7 minus 2u to the power of 5 divided by 5. The limits stay the same. If we plug them in, we will have 2 times 2 to the power of 7 divided by 7 minus 2 times 2 to the power of 5 divided by 5 minus, in brackets, 2 times 1 to the power of 7 divided by 7 minus 2 times 1 to the power of 5 divided by 5. The result is 832 divided by 35 plus 4 divided by 35, which in total is 836 divided by 35. Finally, we have our result. Yay! Like for the integration by parts, here you can see the total task for integration by substitution again, with all the respective steps. Step 5 and 6 will be on the next slide, as they didn't fit here anymore. This is also how you would write it on paper, so let's quickly recap it again. We started with a given exercise, which was calculating the integral from 0 to 3 of x times the square root of x plus 1 to the power of 3 dx. As the square root was really disturbing us, and we couldn't find an antiderivative right away, we decided to solve it via integration by substitution. It is always nice to write this at the beginning and to include the formula. In step 1, we chose what we wanted to substitute. In this case, it was the square root of x plus 1, and we substituted it with the term u. In step 2 and 3, we calculated phi of u and phi prime of u. As you probably remember, to get phi of u, you have to solve the equation from step 1 to x. For phi prime of u, you only have to build the derivative. In step 4, we calculated the new limits of our integral. We did this with the help of phi of u and the limits from the original integral. And we ended up with b equals 2 and a equals 1 here. In step 5, we had to calculate f of phi of u, and therefore had to plug in the terms from phi of u for each x of our function f of x. In the last step, all we had to do was plugging in all terms into the specific location and then calculating the integral. Seems like a long birth, but finally we came up with a result. Let us summarize this again. Integration by substitution is a really nice method and a good option when part of your function that you want to integrate is disturbing or too complex to antiderivate. This can often be the case for chain functions. I would agree that integration by substitution looks quite complicated at first, but if you stick to the rules and all the steps, you will manage to do it. And then it actually is not too complicated anymore. Again, it is important to remember the formula and the steps here. Another thing worth mentioning is that there are several ways of how you can perform integration by substitution. In fact, there are even different formulas for the different approaches. Of course, they all will end up with the same results, but still they can differ a lot in the actual steps. The one you just learned here is probably one of the easiest ones, so I would suggest that you stick to that one. However, using other ones is also, of course, totally fine. And this is already it for the input of this video. On the next slides, you can find 2 exercises for practice, with which you can try to practice integration by parts and integration by substitution. Here you can see the 2 test exercises. I would highly recommend solving them, as learning by doing seems to always be a good option when it comes to mathematical formulas. The first one should be solved with integration by parts, and the second one using integration by substitution. The solutions can be found on the next slides. I will also go through them and shortly explain the different steps. Here's the solution to the first exercise. Given was the integral from 0 to p of x times cosine of x dx. It is a product of 2 functions, and we will solve it with partial integration. In the first step, we assign f prime of x and g of x. we will have the options x and cosine of x. As x has the easier derivative, we will choose it as g of x and therefore choose cosine of x as f prime of x. The antiderivative of cosine of x is sine of x, and this is our f of x then. The derivative of x as 1, so this is our g prime of x. In step 3 and 4, we plug in the terms and calculate the result. I will not go through the steps here in detail, as it is just normal integration, as you should know it by now. But feel free to pause the video and recap the steps though. The final result should be -2. And here's the solution to the second exercise. Given was the integral from -1 to 2 of x plus 1 to the power of 2 dx. Although you could also multiply this out and then use normal integration, the task here was to apply integration by substitution. In the first step, we define what we want to substitute. In this case, we choose x plus 1 and substitute it with u. In the second and third step, we calculate phi of u and phi prime of u. We do this by solving the equation from the step 1 to x. This yields u minus 1. This is our phi of u. Phi prime of u is its derivative, which is 1. In step 4, we calculate the new limits. We know that the limits from the original integral are -1 and 2, and we also know that they are defined in the formula as phi of a and phi of b. As we know phi of u already, we can plug in a and b and the respective results. If we solve these two equations to a and b, we have our new limits. In this case, a is 0 and b is 3. Now on to step 5. Here we calculate f of phi of u. We know that f of x is x plus 1 to the power of 2, as this was given in the task. We also know phi of u and can plug it in for x. This yields u squared as the result for f of phi of u. In the last step, we plug all the terms into our formula and calculate the integral. Finally, we will reach the result, which is 9. Again, feel free to pause the video for a moment and go through the steps. Alright, that's already it for this video about advanced integration. By now, you should know what integration by parts and integration by substitution are, when you can use which one of them, and how you can apply them. This means you should now be able to calculate any given integral on your own. I hope you liked this video and see you again next time.